go. Actually, let me pause. Okay, so on problem numbers 1 through 10, yeah? You were supposed to summarize your directions. Hopefully you guys had that. We talked about it yesterday. In the sense that for summarizing the directions, we said something to the effect of pre-calc or calc. Pre-calc, you were supposed to solve. Calc, you're supposed to explain, right? If it requires calc, explain why you think it needs calculus, and then estimate in some way, shape, or form. So for number 1, when you guys were doing it, we talked about it briefly yesterday. You might want to write in colored pen that for number 1, you need distance equals rate times time. Distance equals rate times time. And so when they gave you the distance, there we go. You were able to go ahead and take the rate, multiply by the time, and get the 300 feet. Pre-calculus, solve it, done. Number 2, calculus was required because velocity was not constant. That's exactly what I would have said, because there was an equation for velocity. It was always changing. Now, guys, is 300 feet the only way that you could have approximated this? No. But how did they do 300 feet? What's 20? How'd they get 20 feet per second if they gave you like a whole equation for velocity? Did anybody find that on their own? How'd you find it, Nick? Plugged in time? Plugged in 15 seconds? Okay, so if you plugged in 15 seconds to the velocity equation, I think it was something like, wasn't it 20 plus? Okay, so 26.76 is how fast this object is going at 15 seconds. So you could have used 26 point something, something, something as your velocity. So you didn't have to use 20. You could have used 26 point something, 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 how fast it was going after 15 seconds, and that would have given you one estimation. But why did they choose 20? Not 26 point something. That is a valid, like that's one way. What does cosine do? What values does it go between? Good. If cosine goes between 1 and -1, if cosine is the highest possible, what's the maximum velocity? 27, because 7 times 1, the biggest cosine can be is 1. 7 plus 20. 27 is the maximum velocity in this model. They didn't choose 27. What's the lowest cosine can be? Right. It can be 0, which would make it 20, but it can also be -1, which would make it 13. So the fastest this object can go is 27. Not the slowest, yeah, the least fast that it can go is 13. But what did it choose? It chose the average, or it chose the middle of cosine was 0. So sometimes it's going 27, sometimes it's going 13. It was like, on average, it's going, if it's going back and forth, it's going 20. So that's why they chose 20. You could have also plugged in 13 feet per second times 15 seconds, and then 27 times 15, the slowest and the highest in the sense of the fewest number of miles, the most number of miles, and average those two. But it would have been the same. I just wanted to explain to you guys, because I know that some of you guys are like, where'd the 20 come from? I don't know what's going on. So for the estimate, they went ahead and thought through the different range of velocities and chose something in the middle. But if you chose 27, if you chose 13, if you chose, like Nick did, 26 point something, what's going on at 15 seconds, that would be an approximate. But probably the average velocity was the easiest one, or the best one. On numbers 3 and 4, did you guys see why I gave you the clue that I gave you? What were they asking about on both 3 and 4? Rate of change. And what did I say yesterday? Rate of change, think slope. So why does this one need calculus to find the rate of change at 2, and this one doesn't need calculus to find the rate of change at 2? Top one is changing, or bottom one is constant. Can you find the slope of a line? Yes. Could you have taken 2 that way? I suppose, but what was in the equation? Y equals mx plus b. What was your m in number 4? 0.08. Good. So the rate was just 0.08. Why? Because the slope of this line is always the same, and it's the m. So then, how do you estimate the slope at 2? They didn't even draw the tangent line. Well, what did your summer packet tell you to do? What's a tangent line? It's a pencil against a curve. Now, yesterday someone was in here and we were doing this and I got out a ruler because it's so much easier than a pencil. I got out a ruler and I tried to put the ruler on. But you could do a pencil too. And if we did a pencil, it's a little too steep. Where's 2? There it is. It's hitting 2, right? Now, as I hit 2, you're trying to think of the slope of this. I know it's weird. I know it's awkward, but we're trying to think of the slope, right? So I see it. Here's 0. So I need to go over 1, 2, 3 to get to 0. Do you guys agree? 1, 2, 3 to get to 0. So I think that this line hits at -1, 0. And then it hits at 2. What do you guys think that 2 is? Maybe a half? Do you agree with that? 2.5? So it kind of looks like to me that, is this going to work? Nope, Mrs. Christensen changed it. Okay. Struggle. So if this one is 2.5, and if this one is -1, 0, and that looks approximately to be the tangent line, then couldn't I find a slope between 2 points? So all you needed was a pencil to approximate that one. The other way is that you could have seen it's going to run 1, 2, 3 and rise 1/2. So you could have also just kind of cheated and said, hey, it's going to be rise over run, which ends up being 1/6. You could have also plugged in your y2 minus y1 all over x2 minus x1, and you might see it's the exact same thing. Now here's the tricky thing. For number 4, what did the book do for number 4? Did you guys already check that one? What? 0.08. Not number 4, sorry, number 3. 0.16, just kidding. 0.16, how did they get a nice pretty decimal? If you divide 1/6, it's 0.1666666, so it's even different than the book had. Guess what? The book knows. What's the title of the book? Yeah, the book knows calculus. So the guy who is doing this answer key knows. So what did they do? They got the perfect answer, little cheaters, right? They got the perfect answer. So does yours have to be 0.16? No, I think someone yesterday, we did the pencil and we did it really fast and was like, I don't know, maybe up 1/2, maybe 1/2. So maybe you had 1/2, maybe you had 1/4, maybe you just I don't know the slope of the line, but now you could have made a better guess. It doesn't have to be 0.16. Whenever calculus is required, you're estimating. Did you at least get somewhere in the 200s, 300s? Did you at least get something like some sort of fraction? So don't just go copying what they have, because how would you have found it? You don't know this calculus necessarily. This is crazy stuff coming in chapter 2. Okay? It's all right to estimate. Then all of a sudden, hopefully it got a little bit easier for a while, because what was going on in these ones, guys? Area. Hey, can we do that without calculus? Okay, what's the area formula for a triangle? Cool. What'd you guys find for the base? Counting the little tick marks, hopefully. 5. What'd you get for the height? Hopefully counting the tick marks. 4. Good. So 1/2 5 times 4, which is why, well, you could have already checked that one. But that one does need pre-calculus. Plug it in, you're done. Number 6, why did it need calculus, though? Look at your picture. It should be on your page, right? There's a curve. Good. There's a curved boundary. So the curved boundary, I don't know. What'd you guys do? Did you get 5 perfectly? Probably not. Maybe you did. Depends how you did it. Now, the problem is the shading didn't show up in my little PDF picture. So what were the boundaries of this? Can you guys tell what you shaded? -2 to 0. Okay. So if you did -2 to 0, could you have done like a rectangle? And could you have said, okay, -2, that's the distance of 2 for the base. For the height, I don't know, what'd you guys choose? Did you choose 2? Yeah. So 2 times 2 is 4. Should it have been a little bit higher? Sure. Could you have done 2 times 3 is 6? And what's the average between 4 and 6? 5. So maybe you could have done that way to get the 5, or maybe you would have guessed 4, maybe you would have guessed 6. That's okay, you're estimating. Nick? That's okay too. Did you go this one and then do like another one here? Oh, here. Okay. Okay, that's not bad at all either. So then Nick was like, what if I did a base of 1 like we did yesterday and split it up? So do that 1 with 3. 1 times 3 is 3. And then 1 times 2 is 2. 3 plus 2 is 5. That's a great estimation. Yeah. Yeah. But long story short, did you have to have the number 5 as your estimate? No. Were you supposed to think of some sort of shape to fit in there and like try to approximate? Yes. So maybe you had some decimals. Maybe you did it a few different ways. But let's go to we kept on going, right? You guys good? Calculus, pre-calculus, pre-calculus, calculus. Do you agree? Now you might have said pre-cal on this one. Why? What's the shape look like? It looks like a square, but couldn't there be a little bit curved boundary right here? So technically, since there is a curve, even though it looks like a square, and a square would be a great estimation, what'd you guys do? 2 times 2 is 4, right? Oh no, it's by halves. My bad. It's by halves. So that'd be 1 by 1. Sorry, the area should be 1. I didn't realize it was going by halves. So the square is a great approximation, but technically calculus, pre-calculus, calculus, pre-calculus, and you guys can go ahead and check what they did as far as estimating the areas. They used a square and a triangle. Just see if you got around 18. Did you do 15, 17, 20? Did you get around there? They decided to fit in a square and a triangle. Number 8 should have been perfect, though. You should have gotten pi r squared, 2 pi as the final. You would have had to do a little distance formula to figure out the radius. Number 9 was also pre-calculus. You could have either tried to do like a trapezoidal sort of thing, or you could have just done rectangles and triangles. So these two should have been perfect, 2 pi and 27. Number 7 could have been an estimate, and then number 10, they just did the square. But they still call it approximate because there technically were curves on the edges of that. Any questions on any of the area ones? Okay, how many of you guys thought the area ones were kind of nice, like it was kind of easy? Okay. Then we kept on going. Sorry, now I lost track of where we are. What's our next even? Just 18 and 22? Cool, thanks. Why am I skipping the odds? You should have already graded them. Back of the book, and then you could have looked at the solutions to figure out your questions on CalcChat. Number 18, you were supposed to be approximating. There were 2 different ones. There was an under, I think, and an over. Is that right? The bases for the first approximation were pi over 4. And then here are your heights, kind of like we did yesterday. We had to do the different heights. Oh, sorry, there were only 3 rectangles on this one. And then this one, there were 6 rectangles, so pi over 6. We had to split up those bases into sixths. And then they went ahead and used the heights. Now this one split into fourths. This one split into sixths. Where's the other height? I don't get it. Why is it missing? You're supposed to have 4 rectangles and 6 rectangles. Why only 3 heights and why only 5 heights? What was going on in our picture? Did you guys notice what happened at this one when we would go to plug in and find the rectangle height? What's the height at pi? 0. So we had a 0 at the very end. So that's why you only see 1, 2, 3, even though we were cutting it into fourths. And that's why you only see 1, 2, 3, 4, 5, even though we were cutting it into sixths, because the last one is just approximating with a 0, which doesn't really change anything. And last but not least, our last even was number 20. Oops, sorry guys. Where is he? Oh, he's way over here. The match is A. All right, questions that we want to ask on evens or odds remaining. Evens or odds remaining. Anything you put a question mark, just raise your hand and then ask. Yeah, AJ. 13, cool. Same? Oh, 2? Yeah, but not for long. 2 and 13. Anything else? Yeah, Ruth. Okay. So for number 18, we'll start there, then we'll go back to number 13, right, AJ, and then we'll go peek at number 2 one last time. So for number 18, here's the picture, right? So like we did yesterday, it's just not quite as pretty. We have to take this distance, which is pi, and cut it into 1, 2, 3 fourths. So then that's why this one was going to be, oh, sorry, that silly setting. That's why this one's going to be pi over 4, then 2 pi over 4, 3 pi over 4. This one, we cut it into 1, 2, 3, 4, 5, 6s. That's why this one's pi over 6, then pi over 3, pi over 2, 2 pi over 3, 5 pi over 6. And so each of these bases is going to be, because they're all the same distance, each of them is going to be just pi over 4. We're trying to do rectangles. We need bases and we need, what else do we need for rectangles, guys? Heights. And how do you get heights from yesterday? Plug it into the function. So in your calculator, you could have done this guy by saying, okay, every single base is going to be pi over 4. So I can factor out a pi over 4 because it's going to be the base for that guy and that guy and that guy and that guy. But how do we get the heights? Well, we have to plug who into sign? Plug pi over 4 into sign. And for the next rectangle, we're going to have to plug in pi over 2 to sign. For the next rectangle, plug in 3 pi over 4 to sign. And then technically we do have one more space, but if we plug pi into sign, what ends up happening? It's just 0, which is why it wasn't in the answer key. So the answer key had root 2 over 2, 1, root 2 over 2, and then that wasn't there. And so what they did is it was base times height, base times height, base times height for 1, 2, 3 rectangles. Does that kind of make sense? The only thing that's going to change on this guy is that now all of the bases are going to be pi over 6. So for each of the distances, all of those are pi over 6. And then now, what are we plugging in to sine for each of the heights? I'm not going to do each of them, but sine of pi over 6, sine of pi over 3, sine of pi over 2, 2 pi over 3, 5 pi over 6, and sine of pi is 0. So that's how they got 1/2 root 3 over 2, 1, root 3 over 2, 1/2 as their values. Is that cool? Yeah, so you just have to think base times height, and to get heights, we plug into the function. Ryan. Oh, I thought you had a question, Ryan. Sorry, you're just fidgeting. Okay. Okay. Number 13. All right, AJ. Where'd you get stuck on this one, kiddo? Okay. This was a lot like the group exploration. Can someone else, just because I've been talking so much this morning already, can someone else talk through just how they use the group exploration that we did 2 days ago in order to do number, or at least to get it set up, number 13? I'm not going to do the whole thing, but how'd you guys use our group exploration? Or just what did you do? Sorry, I thought that that would be a good lead-in. Yeah, Thomas, what'd you do? So you had to get your square root of x, right? From the basic graphs. So 0, 0, 1, 1, 4, 2. So we can get our basic graph. And then we have the point 4, 2, and that's our point P. Like in your group exploration, which is in your notes, the point 1, 1 was that point, right? And then they want secant lines going from the point 2. Well, they want 1, and then they want 3, and then they want 5. So secant lines, that's like what we did in our exploration too, in the sense of drawing a line, if I can make it even look somewhat nice. Drawing a line. Oops, that's still red. Oh well. So then drawing secant lines that cut through the graph, connecting points. And then they want us to find the slope of each secant line, just like we did in the exploration, in the sense of what's M1, the one that goes through the point, what would that be? 1 and square root of 1. And then 3 and square root of 3. And then 5 and square root of 5. So just like we did in the exploration, find the slope between these two, the slope between these two, the slope between these two, and what were you supposed to be trying to think of? Are those slopes approaching something? So just like the exploration. Okay. And last but not least, number 2. So Rebecca, did it make sense that cosine goes in between -1 and 1? Okay. What you did when you got 26.76 is you figured out how fast this thing was going at 15 seconds. The problem is it wants, for distance equals rate times time, it wants the velocity the whole 15 seconds. So the trouble is you can use a 26.66. That's what Nick did too. Plug in 15. That is a velocity that the object hit at some point. And you could have been like, oh, they were going that speed? Sure, I'll use that one. A better approximate would say they're going back and forth between 13 miles per hour, feet per second. Sorry. They're going between 13 and 27. The lowest they go, -1, is 13, 20 minus 7. The highest they go when cosine's +1 is 27. So 13 to 27, they're kind of going fast and slow and fast and slow. So then saying, well, what's in between 13 and 27? 20. That's why the book used 20, because it's going back and forth. You chose 26 point because it is going that speed at 15 seconds. It's okay. It's not bad. But if you think about, oh, it's going slower and faster, 20 might have been a better approximation. But you have an approximation. That's okay. But maybe make yourself a note just about why 20 would have been a little bit better to use. Yeah. All right, we're good. Yeah? Okay, if anyone has any further questions, you need to be able to speak up just a little bit quicker so that we can answer them. Let's go ahead and put the, which one? Okay. This time I'll have grace, but next time they need to be asked earlier. But thank you, Grace. All right. Final answer was, we already talked about, oh, no, we didn't. It was odd. Lo siento. What was the final answer, guys? Ooh, was it A or B? B. There you go. Trying to ask the area of the region shown in the graph. Is it the whole thing? Mine doesn't have shape. What does it go between? 2 and -2? Oh, a little bit further. So the whole like part in the first and second quadrants. Okay. So if we're trying to approximate that, what did you guys use to approximate? Rectangles, triangles? Probably not circles. Okay. So you could have gone ahead and gone about there. Then you could have gone, what, about there? And then maybe like about there. That wouldn't have been too bad a one. So this one would have been a distance of a base of 1 and a height of 1, 2, 3-ish. This one would have been, I guess you could have split this into 2. Base of 1 and a height of 5-ish or 4.5-ish. We'll just do 5 for now. It's going to be an overestimate. This one, 1 and 5-ish. And this one, 1 and 3-ish. So that would have been 16. But if you guys look at this one, if I was to do 5 for that guy, it's going to be an overestimate. And we've kind of left out these two areas, even though we have these two. I would have thought that 16 was an overestimate, so I wouldn't have gone to 18. I don't want it here. I would have gone down to 14, because 16 would have been a little bit higher. You could have also done something like, that doesn't help. I don't know if you guys thought of this. We could have also done something like a triangle. Oops, sorry, the 2. That would have been a base of 4. And a height of 5. That's 20 divided by 2, which is 10. But that's under. That's too low, right? So that's too low. You could have done a rectangle. Which would have needed to go a little bit past, which would have been, what, 1, 2, 3, 4. A little bit past if I was to do another one, maybe 5. So 5 times 5. It's not quite 2.5, maybe just 4 times 5. 4 times 5 would have been 20, which is too big, so no, that one's too big. The problem was picking between those two. And the way to pick between those two, I think the easiest way was just to split it up into rectangles and see that it would be an over approximate, which is why I went down and not up from 16. But you could have at least gotten down to a 50% chance of getting it right just by using like one shape and one shape alone. Which is pretty good odds as far as like an AP question. Nick, go ahead. Let me get notes open so people can start taking them, but yeah, go ahead. Like a fractal, sort of? Theoretically, because you would also like infinitely approach. The problem is areas of circles are going to be way harder to approximate than areas of rectangles. And rectangles you can do in a systematic approach of us taking the interval and splitting it up to get bases, whereas circles it's going to be totally, in a sense, at random. You could draw it, yeah, but as far as actually solving, there's no like systematic approach to doing it. Does that make sense? Yeah, but no, you're totally right. That would be another way of filling the space. Yeah, what he's thinking of is like the infinite caravan of camels and the, yeah, you guys remembering the Abraham Lincoln with the pennies and all that stuff with by heart. All right, section 1.2. The nice thing is we're only supposed to start section 1.2 and it is reviewed from the summer packet. Finding limits graphically and numerically. And so some of you, as you're going over your summer review quiz, you were like, I didn't get all the limits problems right. Or maybe you did, but I didn't ask very many limits problems. It's good and bad that you guys saw the limits in your summer review packet, because some of you are like, psh, these are easy. I got it. I saw it in pre-cal. We saw it in the summer packet. But every year, the limits test is one of the most brutal in that everyone underestimates it. Did you guys hear that? The limits test, the first full test. The summer review quiz was like a half test, and you kind of got your score offset by hopefully a really good score on your handbook just by trying it and grading it. The limits test, the first full test. After covering each of these sections and doing just kind of more normal math homework where it's not as weird and abstract as the homework you just did, which was this huge preview of what's to come. We're going to have normal homeworks where we cover examples, and homework are like the examples, so it's nice, straightforward. The limits test, everyone always underestimates. Thinking it's going to be easy, and then it just kind of whops them upside the head, kicks them in the butt. Humility happens, whether or not you want it to. So, from the very beginning, don't underestimate it. Dig in, work hard, pay attention in class, work through that homework. It'll be all right. It's not going to be brand new stuff, which is really nice. Nice thing is, pre-cal kids, you already saw this first slide because I already gave you the informal definition last year. There are a few keywords in this informal definition as you write it. We're not going to make it a forever. This isn't something you have to be able to like state back to me all year. It's not like that. But it is the idea that limits f of x's, which are what kind of values? What kind of values are f of x? Function values, good. Otherwise known as y values. Are we okay with that? F of x values or y values are becoming arbitrarily close to a single number, L, from either side as x approaches a. If that is true, if the y values are becoming arbitrarily close to a single number, a single position or location or height, a height or a y value L, as x approaches a from either side, the limit of x will exist. This is where we started shortcutting this big old informal definition to make it shorter. The limit of f of x as x approaches a is L, and shorter, f of x approaches L as x approaches a, and shorter, or more proper, the limit as x approaches a of f of x is L, provided the limit exists, provided as you approach from either side, the f of x will be, or is, getting closer and closer to that constant. So this is the notation. The nice thing is it shouldn't be near as new this year as it was last year. Are we almost there? Now, just a few of you guys, and I didn't take off points. I probably should have, but I hadn't taught you the summer review packet. I just went over answers to the summer review packet. I should not have given you full points on number, I think it was 9A and 9B. Was that the limits one? A number of you, I should not have given full points because you stopped writing limit early. And some of you, it totally messed you up because you didn't finish to the end and you gave me an equation as a limit answer instead of a number or a constant. So some of you, it literally messed you up, and some of you, it could have messed you up, but you somehow figured it out and pulled it out at the end. But this limit notation is super important in that we cannot take the limit notation away, just like we can't take away a random square root from a problem until we deal with it. We can't take this limit away from a function or from an expression we've actually been able to plug in and solve. But we're getting to that another day. Numerically, yeah, there's illustration, the fractals on my wall. We talked about it last year. MC Escher's drawings, different fractals, etc. That's cool that Nick brought that up today as far as the fractals and the circles and Sierpinski's triangle and all that stuff. But we're getting into the math. And the nice thing is, section 1.2, you guys get to go back to solving limits by tables and by graphs. So you're not even necessarily doing things algebraically. Now, you guys have seen enough with the summer packet and with last year, with factoring and canceling out and 0 over 0, keep going. You can check answers. I don't mind the algebraic way. But you are going to have to deal with these with tables. And so numerically using a table, in order to figure out whether or not the limit exists, we're going to be examining closer values as x gets closer and closer to whatever number we're approaching. So as you guys are setting this up, I'm going to go ahead and make this table particular to the example down below. Horizontal tables, way easier to fit into your notes and to fit into homework because it's just going to take up a couple lines rather than like cutting through all these lines. And really quickly, this is an aside, but hopefully it's an important aside. I'll give you a couple more seconds before I explain my aside. Some of us, the way we do homework is so messy. So messy. So right here at the beginning of the year, I'm going to ask and enforce a quick logistic just in homework formatting. Okay, homework formatting really fast. The reason I'm showing you guys the horizontal table is because, once again, it's so much nicer and easier to fit into your homework if you're going across as opposed to like cutting. But some of you do like to go down in like columns. If you choose to not have number 1, number 2, number 3, number 4, number 5, number 6, number 7, number 8, if you like to do columns, you cannot do columns unless you take your little paper and you fold it. And you have half the problems on or some problems on and then the other problems on the other half. When you guys try to do like 1 and then 2, 3, 4, 5, 6 and then 7 and then 8 and then 9 and then 10 and then 11 and then 12, TAs aren't going to grade that this year. That's just ridiculous. Be organized. If you're going to use columns, fold the page in half and then just have it nice and neat. Does that sound good? Okay. Sorry, pet peeve from last year. It was rough. Okay. So if we're trying to approach, wait, what is X approaching? I wasn't at anyone. A lot of people did it. I'll read a question. Go ahead. I would prefer not. If you're going to do that, I always grade homework down. So do like 1 through 5, 6, 7, 8. Like, that's what I would do. There were some people that did that too. And I was like, oh my goodness. Whew. We did it and we did our best. But yeah, it's a lot nicer if everyone just goes down the page. But if you do want to like squish it in and then have another column, just fold it. And that's fine. That's fine. Okay, what's x approaching? -1. Do you guys remember? If you're coming from this direction, and do I want you to be coming from below -1 or above? What do you think? Good. From below. What's a number below -1 on the number line? -2. Good. But we're going to get a whole lot zoomed in, a whole lot closer than -2. So how about -1? What does that mean? A -1.01, a -1.001. I'm going to go ahead and get my calculator. Oh, bummer. Get my calculator opening. There we go. I need to attach that to my home screen or my toolbar. Let's see if that helps. Just to make sure that the settings in your calculator are good. But then, guys, what are we going to be doing as we come from the other direction? Good. -0.9, -0.99, -0.999, right? We're going to be coming from above, not from below. Technically, when you're doing a limit, you're not actually looking for what's actually happening at -1. Now that we've done some work, we know what's happening at -1. If you plug in -1, you would end up with +1 plus 2 minus 3 all over 0, which is 0 over 0, keep going. AKA, there is a hole at x equals -1. So we can tell with a little bit of plugging in work, we can tell what's going on at -1. There's going to be a hole. This actually does not exist, but a limit does not care about whether or not the diner is open. Using our illustration from last year. It doesn't care whether or not there's an actual point at -1. What it cares about is the approach. Good. So is the approach, if we're using a table, and if we're not going to use the algebraic method, this whole introduction to limits is letting us go back to tables, we would go ahead and plug the function into our y equals. Because plugging this in over and over and over again is going to be quite tedious. We can use that cool trick to getting a fraction, alpha y equals. I know some of you guys, a lot of you guys hopefully already know this trick, but for those who haven't had me before, maybe they didn't know the hidden cool fraction bar. We're going to plug in our function. And then guys, what do we do in order to let our table go by differing amounts, different steps? Go straight to automatically generate? No. We need to go second window, good. And we need to make it not automatically going by ones, but ask. Good. So second window sets up the table, and then we can go ahead and hit ask for independent, and when we go to second table, now it's going to say, what do you want? And I'm like, oh, let me tell you. I need -1.1, then I need -1.01, then I need -1.001. What seems to be going on? My button or your button? Oh, it's because the recorder's on top of it. No, it's okay. I know it's weird. It took me a second because I was like, oh no, I'm going to stop the recording every time I hit the 0, but then it started working. So as we fill in our table, we have -4.1, -4.01, -4.001, I think, double checking. Then we have -3.9, -3.99, and -3.999. My graph does not exist at -1. Something is missing, but looking at the approach, can't we tell what's going on? This is approaching 4. What would happen if we were to factor and cancel out the x plus 1s and then plug in -1? You get 4. That's the algebraic way. But we're remembering how to do it with a table. Yeah, AJ. Thank you. Did I not put the silly me? Thank you. Thank you. Why did I not write the limit again? Ooh, some of you should have lost points on the summer review quiz. Why did I not write limit and then -4? This is the answer. Good. Limit is telling you what to do, what to take, what to find. Once I solve like an equation with the square root should be gone. It should just be x equals. So the same thing. This whole thing is equal to -4. I'm done. Now, that's for numerically. Let's just jump ahead to graphically. Because graphically, this is a lot like the one that we just saw. It's not exactly the same. This looks like a square root function, I think, right? F of x looks a lot like a square root function down here. That's been shifted up. But it's a square root function with a hole at 1. So as you guys are writing the first little piece, I'm just writing the problem that I'm meaning this graph to illustrate. The limit as x approaches 1 of f of x, does it exist or not? This is one of the most commonly missed limit problems on any practice or actual AP. Sadly enough. All you're supposed to be doing with a graph, just like a table, is coming from the right and the left of the a that x is approaching, looking at the y value, looking at the heights, looking at the y values, looking at the heights, and trying to see, are the y values approaching a set single constant? Trying to see, are the y values approaching a set single constant? What do you guys think before we leave for today? Does the limit exist, yes or no? Oh, no confidence? How many of you guys say the limit does exist? How many of you guys say the limit does not exist? What's the problem? It's all about, are the two guys headed to the same place? Yes. Does the limit exist? Yes. Is the diner burned down or closed? Yes. But are they meeting? Are they approaching the same? Yes. The limit exists. The limit is 2. Oh, half of you would have missed it. We'll come back to it tomorrow. Homework is due on Monday. Bye, guys. Homework tonight is start. Bye. I do not have you trained well enough. No one said start. Struggle.